So in this lecture, what we will do? So first, we will determine logic levels using TTL and CMOS voltage profile diagrams. So TTL, you should know it means transistor logic, right? And CMOS, it means complementary metal oxide semiconductors. So it's just families of integrated circuit. Okay, so we'll define the voltage profile diagrams of this both type of integrated circuit. Next, we will use some selected TTL and CMOS devices, and we'll just watch their input and output voltage, and also we'll see their noise margin. Okay, so understand other IC specification, because except voltage, there is other very important parameters of the integrated circuit, such as drive capability. It means how much current it can take and how much current it can go outside. So fan in, fan out, this kind of terminology. Propagation delay. Propagation delay just means, speed operation, and the power consumption, how much energy integrated circuit consumed during its operation. Also, we list some safety precautions, but mostly you should read it in the chapter 5. So I will not cover this one, but when you will read, you will find. Okay, next. Recognize several simple switch interface and bouncing circuit using both TTL and CMOS integrated circuit. Actually, tomorrow in the lab you will do this kind of works. And analyze interfacing circuits for LEDs and incandescent lamps. So incandescent in Russian means накаливание, да? Incandescent lamps, it's just these old lamps, лампы накаливания, да? Using both TTL and CMOS integrated circuits. So we'll consider some. Actually, you perform this kind of work on lab by using multi-slim. But anyway, we'll cover this topic. Explain the basic of current sourcing and current sinking. So you should understand what is a sourcing, what is a sink, not thinking in terms of think. Sometimes for us it's difficult to pronounce. Sinking, not thinking, okay? Sink, по-русски, да, it means тонуть. Okay, you need to understand this kind of terminology, what means sourcing and sinking. And also, we will draw some TTL and to CMOS and CMOS TTL interface circuits, because for now in labs you use only TTL or maybe CMOS, but sometimes we need to connect this to kind of integrated circuit, and it's not easy. You should understand how to do it in the digital systems, because their voltage, their current capabilities is different. Describe the operation of interface circuits for buzzers, relays, motors, and solenoids. So I think this part is very interesting, because it's meaningless to study the digital system, just study the integrated circuit, but do not use it. So our goal is to drive some outside devices, for example, some buzzers, relays, motors, and solenoids. So actually, it's the goals of any digital systems. They should give us some output. So output may be some kind of information, but it can be some kind of action. For example, when motors will work and do some work. And analyze interfacing circuit featuring an opto-isolator. So we consider some interesting device. It's called opto-isolator. So actually, it's work as a relays, but it's a little bit different. So we'll understand what is opto-isolator. Also, we'll describe a servo motor and summarize how it's controlled using pulse width modulation. I hope in the future in your curriculum you will have more advanced courses, for example, embedded system, and you will, for example, maybe you will work with some microcontrollers. For example, Arduino is very popular, and actually you can buy some interesting kits and connect some motors to Arduino and just program, and this motor can do something that you want actually. So understanding how servo motor works, will be useful for you in the future, because maybe some of you wanted that his career was connected with programming some microcontroller. So understanding all of these things is very important for you. And also, I will highlight it with red. You need to read it yourself on the book. So, okay, so let's start. Integrated circuit specification, simple interfacing. So, you should know that integrates, we have actually two big families. What kind of families we have? Integrated circuit logic families?
TTL.
Yes, TTL and CMOS. TTL stands for transistor logic. So it's based on the bipolar transistor technology. So, and also CMOS, it means complementary metal oxide semiconductor. It's based on other technology. So, but both type is very popular, but CMOS now becoming is more widespread because there is some reasons for it, and we will talk about it today. And integrated circuit within a logic family are designed to interface easily with one another. So actually, when you work, for example, only with some TTL family, actually it's easy to interface. But first we need to understand what is the interface. How do you understand what is the interface? Interfacing can be defined as the design of interconnections between circuits that shifts the levels of voltage and current to make them compatible. So actual interfacing, it means interconnection. It means actually connect two devices. So, but why we need to do interfacing? Because the parameters of two devices can be different, voltage, current, and other things, and we need to, come up with some circuits that will actually make sure that voltage and current are compatible. Compatible in Russian means сопоставимый, да? Okay, interfacing between logic families and between digital integrated circuit and outside world is a bit more because voltage, current, they're the same. But when you're working with different families and when you want to connect your integrate some circuit to some output, some device, you should think how to properly connect them. It can be complicated, but if you understand the voltage, current, and other parameters, it's not so difficult to handle. Okay, so most logic circuits are of no value. They are not interfaced with real-world devices. So actually, it is a goal of digital system. Any digital system, they're interfaced with real world. For example, our computers, right? They give us some useful information in terms of video, audio, some text. So it's meaningless to work with it, and when we don't have any real-world applications. Well, logic levels. In any field of electronics, most technicians and engineers, I don't know, maybe someone of you will in the future will work as engineers. So engineers, it doesn't mean that IT also, you can say we can say the ITs, it's also engineers because you do some developing on devices, etc. So engineers, it doesn't mean that, guys who works, with some instruments. No, IT is also engineers. So you should understand what's the voltage, current, resistance, and the specification in devices. So let's first start with logic levels of TTL. So actually in the first lecture we talked about this logic levels of TTL. So how is a logic 0 or logic 1 defined in TTL? So do you remember this kind of diagrams? So actually, what is this? Is at the center?
Not.
Yes, it's not logic. It's inverter. So here you can see it's input voltage. So this TTL will understand from 0, from ground to 0.8. So within this range, from 0 to 0.8 volt, it will be low signal, low input. From about 2.2 volt and up to, for example, 5, it will be high. So, but if your signal, if your input will be in between 0.8 and 2 volts, in a defined region, and you should avoid working in this undefined region. But it is input. If you look at the output, here on the output you can see it's a little bit different, right? So the low value here, it's close to the ground level 0, right? So typical value it's about 0.1 volt, and the high output, so it should be 5 volt, but it's not 5 volt because there is some we lose some energy in the inverter. So actually typical values that give us this simple TTL inverters will be 3.5 volt, but it can be as low as 2.4. So output should not be in this region undefined. So you should avoid these regions. Okay, so I think we'll already see and read this in the chapter 1. Okay, so let's consider logical levels for CMOS integrated circuits. They're completely different. So here you can see inverter, for example. You also should read in the chapter 1 or 2, there is some definition. What is a series, etc. Okay, so it is some CMOS ones. And here you can see input signal. So it's different, right? So low can be from 0 to about 3 volt, okay? And but I forget to mention that it depends. Actually, CMOS, they can work from 3 to 15 volts. For example, here we have some inverters that work at the 10 volts. So in this case, low can be from 0 to 3 volt and input, and output can be from 7 to 10 volts, right? This inside it's undefined. So here you can see the output. So here output, you can see that it's very close. High output is very close to the output voltage. And you can see that output low, it's very close to the ground. So actually, you also saw some tables when described in terms of percent, but you should understand sometimes we say VCC. In CMOS, we call it not VCC, but VDD. Okay, I think it's clear. But there is other type of CMOS, because if TTL works in the range of 5 volts, CMOS, as I mentioned, can work from 3 to 15 volts. So here, for example, you can see that this series, it's voltage lower than 10 volts. So, for example, they kind of, similar to the TTL, but the undefined region and this threshold for low and high is different. But the voltage range, 5 volt, is similar to TTL. So, for example, you can see some CMOS inverter from this series 74 HS00 and etc. So you can see that input low can be from 0 up to 1 volt, and input high from 3.5 and to 5 volts. And you can see the output. This actually similar pattern is similar to this one, but just maximum voltage is different, right? Okay, so I mentioned this one. There's other kind of series of CMOS that actually can replace with TTL. So they a little bit different. For example, here it is also CMOS. You can see this series. So input, it's the same as for TTL. So we can see that low can be from 0 to 0.8, and output from 2 volt and up to 5 volts. So the input is the same as for the TTL, but output is not. Output is approximately the same as for other kind of CMOS integrated circuits. So for this reason, you can see this labeling. You can see this T. Can you see here T, here T, here T? T, it means that it is compatible. It's input compatible, comparable with the TTLs. So next, guys, my connection is fine. My voice is clear.
Yes,
Yes.
clear.
Yes.
Mhm.
Yes, it's
Fine. But for example, now we all have the smartphones, some small devices, and they, manufacturer tried to reduce voltage because if the voltage will be less, it means that battery can have the less value, and the energy consumption will be less, because you should understand that what is a current power? Current power is it's voltage times the current, right? So if you will reduce the voltage, it means we will reduce the power, and it means that we reduce the energy consumption. For these reasons, now all manufacturers try to reduce the voltage of the power supply voltage of integrated circuit. So more popular, more widespread is 5 volt, but it's too high. So there is some low voltage CMOS that can work at the voltage less than 5 volts. And here you can see this kind of series 74 LAV, and etc. So LV, it means low voltage. So here you can see the profile, voltage levels profile. So you can see that it can work. So its power supply is 3 volt. So for these reasons, this inverter will understand if you apply from 0 to 1 volt, it will understand it's low. But if you will apply from 2 volt and 3 volt, it will understand as a high. So between this, it's undefined regions. So you can see its output. So output, high output is approximately 3 volt, and you can see that the low output is approximately the same as the ground level. Okay, so now we just considered one specifications of the integrated circuits. We just considered for the inverter, but it is applicable. You can, it's the same for other types. So it's not always true for the inverter, but also for other kind of logic gates, for example, AND, NAND, or etc. We just inverter just as an example. So next we will consider noise margin. So noise in Russian it means шум, noise, it's шум. Margin in Russian it will be just поле. For example, you have some node, and from left or right side we'll have some margin. То есть we can say not noise margin, we can say noise range, for example. Okay, so I mentioned that CMOS becoming more popular, and for example, in any modern device, for example, in smartphone, mostly CMOS is used. Why? Because first of all, it consumes less power, and also it has good noise immunity. So what does it mean, noise immunity? So noise immunity is a circuit's insensitivity or resistant to undesired voltage or noise. It's also called noise margin in digital circuits, in digital systems. So, for example, in any circuit, there is some kind of false signals. Reason why they occur, it's a lot of. It can be from, I don't know, for example, maybe someone doing some. It's difficult to explain, but noise in the circuit, it's widespread, and for this reason, due to this noise, sometimes some digital circuit can work improperly. But before we will talk about this, let's give some what is the noise in the digital circuit and digital system. Noise in digital system is unwanted voltage induced in the connecting wires and printed circuit board traces that might affect the input logic levels, thereby causing faulty output indications. So the noise margin is much better for the CMOS than for the TTL family. So you should understand the popularity and the widespreadness of the CMOS. First of all, it's due to the lower power consumption and due to the it has more insensitivity to the noise. Okay, so let's consider some this kind of profile, but it is not voltage profile. It's we can say noise margin profile. So it is for TTL. For example, here you can see this one, right? It's unfortunately I could not show for you now, but if you recall the voltage profile of the TTL, you know that you should you know what the threshold for the low and threshold for the high. And here, for example, if a typical signal that we apply, for example, in this region, so in this case, our noise margin will be 0.4. It is for TTL, but in comparison, let's check the noise margin for CMOS. Here you can see that noise margin for the CMOS is greater, 0.5. Why? Because this threshold is larger in comparison with the TTL. For this reason, noise margin is 1.5 volts. So it means that in the circuit can be some spikes, some false signals, but if their value is less than 1.5, it will not affect the circuit. And the same with the high output. This here it also has the noise margin about 1.5 volts. But of course it depends what selected CMOS. But in average we can say that for the TTL it has this kind of profile, and for the CMOS it has this kind of profile. Okay, but in actual practice, the noise margin is even greater. So why? Here you can see the other interesting diagram. So actually in TTL it can be greater. It can be up to 0.8. Why? Because, for example, if your voltage, your signal will be higher, will be, for example, I could not see how much this one, 0.8. For example, it can be 0.9, your signal. So, but it will not be switching, because for the switching, for this kind of situation, it should be 1.2 volts. So we call this ones as a switching threshold in the integrated circuits. But do not pay a lot of attention to this switching threshold, because it depends on a lot of things. It depends on the temperature. It depends, for example, what kind of logic gates you're using, a lot of things. So, but manufacturers can guarantee the low value, high value, but this switching threshold is just, it depends of the situation. For example, I mentioned, for example, temperature. Okay. So for now, we considered voltage profiles, we considered noise margin of integrated circuits, and let's next talk about the drive capabilities, because drive capabilities is very important. Unfortunately, you did not study the electronics. So if you studied electronics, you would study, for example, transistors, how it works. But I mentioned that in this course, Of course, it's good if you will know what is a bipolar transistor and other devices from electronics, but actually could understand this course without the strong knowledge in electronics, because in this course we cover some parts, but we could not go to detail because we don't have time. But for example, in electronics, when we work with bipolar transistor, there is some parameters that define its properties. For example, we can say maximum power. Sometimes people call it maximum wattage, but it's better to call it maximum power, and collector current rating. So how much current can this bipolar transistor can give to the circuit or can take from the circuit. So there is some limit to the current. So it determines its drive capabilities. So you should understand what is the drive capabilities. So, but we're studying not bipolar transistor. We're in our digital system courses, we're using integrated circuit. And here we should understand what means some kind of interesting parameter. We call this fan out. So fan out, it's some this parameter actually defines the drive capability of integrated circuit. So now you will understand. So the fan out of digital integrated circuit is a number of standard inputs that can be driven by the gate's output. So for example, let's consider some example. For example, if the fan out for standard TTL gates is 10, for example, we have some kind of TTL gates, it may be some inverter, and we say that it's fan out, for example, 10. This means that the output of the single gate can drive up to 10 inputs of the gates in the same subfamily. What does it mean? It means that, for example, we have some inverter, and this inverter has fan out 10. So it means that we can connect to the output of this inverter 10 other inverters with the same family, and the drive capabilities should be enough that this one integrated circuit, for example, one inverter can actually power 10 other inverters. So, and in terms of TTL, for example, in TTL, in average fan out value, it's about 10. Okay, but for the CMOS, it's completely different. For example, there is low power Schottky TTL. We label it LS. LS, it means low power Schottky. So its fan out maybe 20. So what does it mean? It means that to the output we can connect 20 other inverters. For example, if we work with inverters, and it should work. But it should be the same family. For example, if we will work with the Schottky TTL, so to the output we can connect only Schottky TTL, not others. We could not, connect simple TTL because in this case, fan out will not be 20. But for example, if we work with the CMOS, so CMOS also is better. Why? Because fan out is larger. For example, some series CMOS considered to be about 50, so it's fan out 50. It means that to the output we can connect 50 other CMOS integrated circuits. Okay, so here there should be some example maybe in the next slides. Okay. So now we'll consider some interesting diagram. So here we talk about the fan out. So you should understand fan out is just a number of standard inputs that can be driven by the gate's output. Okay, but also we can look at the input current. So just let's see this diagram. So here standard TTL voltage and current profiles. So for example, we have some inverter, and when its value, from the output, when output is low, it means when output is 0, we can take from this output about 16 milliamperes. Yes, but when the output is high, we can drive only 400. Yes, 400. It's milli. It's microampere. Okay, but it is an output drive. So how much the current TTL can give to the some circuit, right? So you can see when it's low, it can give more, but when its output is high, it gives relatively lower current. So, but it's output drive. So, but also there is the input drive. So input drive. Here you can see that when the input is low, so it means maximum we can have 1.6 milliamperes. But when the input is high, you can see that current is 40 microamperes. Okay, so here you can see what means OH, OL. So OL is that output is low, OH is that output is high, IH the output high, and IL the output is low. Okay, maybe now it's not clear, but now we'll consider some example after this. Okay, so it is a sum table. You do not need to memorize this table, but for example, when we will do some tests, you can refer to this table and find the needed information. So here just we have two families, TTL, and it's some subfamilies, for example, standard, low power Schottky, some advanced low power Schottky, fast, Fairchild advanced Schottky TTL, for example, CMOS, and you can, here in this table, you can find output drive and input loading. So of course, do not need to memorize, but you should know where you can find this. You can find from the slides or maybe from the book. Sometimes people say this label is fan in, fan out and fan in. So, but it's rare terminology. Okay, what's this important? Notice that the fan in or input loading characteristics are different for each family integrated circuit. So this kind of is very different. Some is similar, but this is different. Here I have some problem for you. How do you understand the? So, for example, you're asked if the 74 LS 0.4 inverter has enough fan out to drive the 4 standard TTL NAND gates on the right. So here we have some inverter, and to the output of the inverter we wired 4 NAND gates. So the questions: the fan out of this device is enough to drive this NAND gates. So for it, I will give you this diagram. So please answer to this question, calculate what is the fan out of this inverter. Can you say? Guys?
So there should be 4 different answers?
No, one answer. What is the fan out of this inverter? So this it is for this. So it's, you can see LS TTL output. So it's output for the inverter. This input for this NAND gate. So how can we calculate the fan out? So okay, let's start with when this output is high. When this output is high, it means that this inverter can give us up to 400 microampere, right? Amperes. And let's consider the this NAND gates. So when output here is high, it means that input to these gates is also high. So each the standard NAND gates, they take 40 microampere. So what does it mean? It means that when the output is high in this inverter, it means that it can power up to 10 NAND gates, right? Have you understand the idea?
Yes.
Okay, so maybe you will think that fan out will be 10, but it's not 10. Why? Because you need to now check the low value. So when the output is low, so maximum this inverter can give us 8 milliamperes. But this standard NAND gate, it consumes 1.6 milliamperes. So if you will divide 8 to 1.6, how much it will be? 5? If we'll divide 8 by 1.6. Yes, this will be 5. The fan out of the this LS-TTL gates only 5 when driving standard TTL gates. Have you understand how can you calculate from this kind of diagram the fan out? So it's not 10,
Yes.
it's 5. So can this inverter can drive these 4 NAND gates?
Yes.
Yes, it can, because it can drive up to 5. But here we have 4, right? Okay. So for now, we considered voltage profiles, we considered the noise margin, we considered drive capabilities, and now we understand what is a fan out, what's the inputs current, outputs currents, and you should understand that it's different when it's low, when it's high, they're completely different. Next, parameters of any integrated circuit that we're studying. Also, there is other important parameters called propagation delay. So how we understand the word propagation? Как вы понимаете слово propagation? По-русски как оно переводится? Propagation means, in Russian means распространять, да? Propagation delay. То есть, если по-русски сказать, то есть это задержка передачи, можно сказать. So what is? So actual propagation delay, it's inversely equal to the speed. So speed or quickness of response to a stage at the inputs is important consideration in high-speed application of digital integrated circuit. So let's consider here there is some, for example, we have some inverter, TTL inverter, and at the beginning the input will be low. If the input of the inverter will be low, what will be its output? Guys?
High.
High. So here you can see that output is high. For example, but from this point, you switched, you apply some voltage, and of course it will take some time. You could not actually immediately, raise the value. So actually it will take some time to raise the value. So here you can see some time that input goes from the low to the high, right? So, but you can see that response is not immediate. There is some delay. Can you see here? There is some delay. There is some delay, and after some time, the output will respond to the input, right? But not, immediately, not simultaneously, but with some delay. Delay по-русски это значит задержка. Okay, so you can see that this time between these two dotted lines, we call this propagation delay, and we measure in second, but it's very small, and of course we need to use some prefixes, in this case 12 nanosecond. So nano, you should understand, means 10 power of minus 9, right? But what's interesting here, look, for example, so here you can see that inputs high, it means output of inverters will be low. So here, and from this time you begin to decrease the input, and input will go to the low, but you see that the output will have some delay to respond, and this delay is about 7 nanoseconds. Can you see the difference? They're not the same, right? So actually the input-output delay and how much it means low-high delay and high-low delay is different. So you can see that actually high-low delay is lower. Okay, the propagation delay for the low to high transition of input to the inverter is different from the high to low delay. So the lower the propagation delay specification for the higher the speed. Yes, I think it's clear. If this value is lower, it means that speed is higher because they're inversely proportional. Okay, here's some diagram. It's just some logic families. You can see some here. What on the axis? What on the axis we have? On the axis we have some family, right? Series of families of integrated circuit, and here we have propagation delay. You can see that AC TTL, they working very fast, right? But you can see that some CMOS S series and CMOS series of 4000, their delay is too high. So actually there is one how to say, one disadvantages of CMOS is that mostly standard CMOS, their propagation delay is high, so they respond not so quickly. But if you will take some simple, for example, this TTL, you can see that for TTL, propagation delay is low. So TTL, it's just simple TTL, standard TTL working faster than some standard, standard TTL working faster than some standard CMOS. But of course, there is some CMOS that work very fast. Here you can see. Okay, so you can check on the book chapter what means AC, AS, AC, etc. So actually, it was on the homework. So let's consider last definition. It's power dissipation. Then we'll take some break and continue on the next next lesson. Okay, so power dissipation. You should understand that any integrated circuit, they consume some power. Of course, it's some kind of unfavorable effect, but it consume, and all manufacturers try to reduce this power consumption. Why? Because this power consumption it just generates heat. That's it. So we do not need this heat, and we need to reduce the power consumption of the power dissipation of integrated circuits. So, but there is some interesting connection between propagation delays. If we will try to decrease propagation delays, it means that the power consumption and related heat generation increase. So when we try to, if we will take some fast working circuits, these circuits will consume more power. So standard TTL integrated circuit might have propagation delay of about 10 nanoseconds compared with the propagation delay of about 30 to 50 nanoseconds for this 4000 series CMOS. So in terms of propagation delay, so you can see that TTL, they beat CMOS, but they consume more power because this CMOS 4000, they consume only 0.111 milliwatt, but standard TTL, they consume about 10 milliwatt. So you can see how much difference 1, 2, 3, 5 order, right? Difference 4 order. So it's really big difference. Okay, so the power dissipation of CMOS increase with frequency. So sometimes we need to work with some circuits that operate on high frequency. So when the frequency is high, it also consumes more power. But it's physical. We do not need to answer to questions why, but you should just know this, that when we'll try to increase speed, power consumption increases, and when we need to increase the frequency, power consumption also increases. So that's it. But why it's happening is not the realm, it's not the purpose of this our course, but just you should know it. So here, last for this lesson, what we consider this power dissipation diagram, and here you can see some on the axis you can see power per gate in milliwatts, and here on the y-axis you can see the internal gate delay. So you can see that this fact series the best. Why? Because first of all, the power consumption is lower and also propagation delay is lower. So I think for now we can take a break for this lesson and we'll continue. So if you have some question, you can guys ask. You can ask in Russian during the break.